today, let's get into parallel. So this whole time we've been working through series circuits. We're going to change the rules on you guys a little bit as far as how we find specific things, but fundamentally Ohm's law, Kirchhoff's law, everything still applies and it still works just like normal. So before, when we had series circuits, everything was connected together. We had one current path. Well, the definition, oops, told you I was going to do that. I was jumping right into AC. So the definition of parallel is where we have multiple current paths going throughout our circuit. So in this case, we have two resistors, but they are connected in parallel. Because of their joined together at this node, we can have current flowing this direction, and we can have current flowing this direction. Now, yesterday when I was talking about Kirchhoff's current law, what was that law stating? The current that goes into a node has to come out. So if we have this current, we're going to call it IR1. This current we're going to call IR2. We could also call it IA, IB, whatever. Using Kirchhoff's current law, what's the current going into this guy? Not just similar, it's the sum of them. So our total current is equal to IR1 plus IR2. So kind of like where we had in series, we had voltages that add together. In parallel, the currents are going to add together, because Kirchhoff's current law still has to be satisfied. It depends. It depends on the resistance. So in this case, how we had, the similarities with voltage and everything like that, it would break apart according to the resistance, and we could find that ratio. Current does the same thing, only the inverse. Because remember, the more resistance you have, the less current you have. So in this case, the resistor that's larger is going to have the smaller amount of current going through it, and vice versa. Small resistance is large currents. So when we're looking at these guys, we need to be able to determine what is their voltages, what are their currents, that kind of stuff. So one of the cool things that we have here, so if our resistance is staying the same and our current is changing, what about our voltage? It's going to go down and change like that. But the big thing is, and I think I said that wrong, but the idea is, so we have one part that's going to be changing in our thinking. So before we had our voltage drops, which are changing from resistor to resistor. This case, we have our current drop that's changing from resistor to resistor. So if our resistance staying the same, the current value is going to split. The voltage is going to stay the same here. We can only have one thing that's changing at a time. So series circuit, we have voltage that's going to be splitting up. In parallel, we have current that's going to be splitting up. Voltage stays constant in the parallel network. So, in parallel, so the voltage source is going to be equal to the voltage drop across R1 and the voltage drop across R2 in this configuration, because everything is in parallel with each other. Now, some of the differences that we have and kind of ways to think about this is in your, at home, when you guys plug in Christmas lights. Those are connected together in series. They do have some sections nowadays that they've got them split up to where they're more in parallel. So that way if you lose one bulb, you don't lose them all. But before that, you would lose one bulb and the whole string would shut down because they were all connected in series. Parallel is your house wiring. So everything that you have is going to be wired into parallel with each other. They need the same voltage. That's why if you look, no matter what plug you go to in your house or into the room, when you measure it, it's 120 volts AC, every single one of them, because every outlet is shared in parallel. So the idea behind this, let's see, I'm trying to remember So you got a circuit breaker, okay, in your house, 15 amps. That's connected into your house into all the outlets. So you may have an outlet here, say in your bathroom. Okay, you have a couple of outlets in there. Those outlets are also connected to the outlets in your room. They also could be connected to the outlets in your kitchen. This wouldn't happen. This isn't up to code. But some older houses still have this wiring in there. So all your circuits are connected together. Well, let's say you're in your bathroom, you're doing your hair, you have your blow dryer going, and let's say it's consuming 7 amps of power. Okay, because it's got to get things hot, it has to blow the fan to go in there. What else might you have going on at the same time in different rooms of your house? You could have your toaster running. That's pulling 3 amps. Your fridge, okay, fridge is going to be constant. Come on. That's pulling another 3 amps. I'm just kind of generalizing here. So let's say you have all this going. What is our total current that we are currently pulling through this breaker? 13 amps. Let's say we go into the bedroom. Let's say you have a microwave in your bedroom. They're going to be pulling more current. So yeah, so in this case you have a microwave. Those are going to be pulling another 7 amps. Yeah, you fire this microwave up, what's going to happen? That thing's going to trip. Yeah, cold burrito. We have in my house, we wired up, because we gutted it down when we redid our kitchen to the studs. And we wired in a microwave plug because that was code. Your microwave and your fridge are supposed to be on separate plugs. That way, in case you trip something in your kitchen or whatever, your fridge doesn't shut down. And the fridge should be the only thing on this one circuit, just so it saves your food. Well, we have a microwave wire to it, but we also have another switch or another little, like you said, a power strip that we use for like the mixer and the skillet and that kind of stuff. If we're running our skillet and our microwave, we trip our 15 amp breaker, and we do it all the time because we're making breakfast in the morning. We're trying to defrost some stuff. We're trying to get things butter melted, that kind of stuff. We have our griddle going, and we trip the 15 amps almost every single time. And then I yell at myself because I keep forgetting to do that and that kind of stuff. But the idea behind this is these are all wired together in parallel. Every single one of these guys needs 120 volts. Now, even these plugs themselves, they're wired in parallel with each other. Every single plug has access to the exact same voltage that everyone else has. The times you're going to see it is when you start drawing too much current. Even this is like a 15 amp breaker, sometimes they don't blow when they should. They're old breakers, they stick, that kind of stuff. So they pull more and more current. Things start to get hot, and you're going to start to see your power drain a little bit. Your house has usually they're about 300 amp service. 200 to 300 amp service is a normal house or apartment. So you can pull a maximum of 300 amps through your entire house. So you always got to kind of be conscientious. That's why they put out the recommendations not to put in power strips and be constantly using them. Because for one, if you have a power strip that has, say, 5 plugs on it, and you plug it just into your regular wall, these ones are rated for about 15 amps of current, normally. You start pulling 15 amps through that one device, through that one power strip, you're going to start building up a lot of heat, and that's where things are going to start melting, catching fire. I think the grand majority, probably 70-75% or higher, of house fires is caused by the power strip catching fire. Not anything else, the power strip. because that's what's get overloaded. Everything's coming through that one little device, and it could even be into a 20 amp line, but the box itself, the splitter, is only rated for 10 to 15 amps. So your circuit breaker is never going to trip because you never get over that threshold, but its internal rating is you're going to pull way too much current and melt it. That make sense? Parallel is very, very useful, but it's scary. Yes? Yes. That was why. No, it was honestly a safety hazard. There was probably a little bit of jackassery in there, because if they made you buy a specific brand. Yeah, yes, that's a little bit of jackassery, yes. But the safety behind it is the same. You don't want to overload your circuits, and especially in a dorm room. You've got, they didn't want you to kill each other. And the thing is too, and that's one reason why, like in some of the residence halls, I'm not sure if you guys live there or not, but I know some of them have restrictions that you can't have a hot plate, you can't have a griddle, because they can't pull that much current through it. They didn't build it to support 20 amps of current through every single breaker. Yeah, but the nice thing is nowadays, like with your entertainment devices, TVs used to be a big problem. Like those great big tube TVs, those suckers pulled current like a mother. Like those things are power hogs. Nowadays, you get the LED screens, you're talking, power-wise, you're talking like $5 a year to power the TV. The other ones were like $5 an hour. So. It depends. It just depends on how they set them up. You could. They have meters you can plug in that'll show you how much power you're using through that plug.
Because I have a power strip that has 10 ports in it, and I have yet to use all of them at once, and I don't think I'm going to ever.
I would try not to, because then you have to figure out where the breaker is. If it's ISU, then you got to call maintenance. Maintenance has to come up and flip the breaker, and you're going to be spending probably the next 3 hours waiting for maintenance to show up. I don't mean that rude or any way. It's just yes. Mm-hmm. Surge protectors are for like lightning strikes, transformers blowing up, things outside of your control, pushing large amounts of current in there. It protects itself to keep things downstream.
So basically, just the second it current spikes, it shuts down.
Mm-hmm. Yep. I saw another hand. Okay. Uh-huh. So we have 13 amps before our microwave. So remember, all these currents are going to be flowing down through each of these channels, each of these branches. Okay. So this one's going to be pulling, your fridge is pulling 3 amps, your toaster's pulling 3 amps. So that's a total of 6 amps running through that branch. This one, until we turn the microwave on, it's not pulling anything. This branch is pulling 7 amps. And so our current total is equal to the 7 amps plus the 6 amps, which gives us a net of 13 amps. The total before the breaker will pop is 15. This is a circuit breaker, not a current source.
Okay, but then everything going on that's like below it, so that's not going to blow up.
Yes.
Okay.
Yeah. So anything below this value will be fine. Even if you get to 15, it's not necessarily going to blow. You could get some of these that blow at 14.8. It's just all about the tolerance. Plus, you're going to get some that they detect a huge surge in current, and that's when they'll trip. But if you slowly ramp it up, sometimes those won't trip until you hit 20 amps. So you can get a 15 amp breaker to not trip until it hits 20 amps if you go slow enough. Yeah, because you're instantly powering it up. Now, if you started out slow and slowly increase the temperature, we could probably get away with it. But usually our skillet's running hot. We hit start on the microwave, it fires everything up, and you trip your breaker. Yep. And honestly, the thing is we have a tenant in our basement, the apartment that we rent out. And as of yet, he's yet to trip a breaker. First time I move into an apartment, I trip a breaker because, for one, I don't know how much I can push it. But it's been funny. We haven't had a single problem with any of those breakers being tripped, which is nice because we haven't had to respond to anything like that. So,
So like, what's your best way to trip a breaker? Like, how do you do that?
to reset a breaker?
No, like if you said you like to.
Oh, usually it involves turning on a microwave and firing up your skillet at the same time. Those two things will draw a lot of current.
How do I know which being a microwave is supposed to be?
Which circuit?
Yeah.
That's you have to figure out. It should be labeled.
Oh yeah, my circuit.
Should be labeled. Ours doesn't have a cover or the front or even the front panel to it, like all the wiring's exposed. So yeah. So we don't have any kind of list. Luckily there's some drywall onto the side, like inside of a wall, that I've slowly been writing down as we trip things and as we shut things off. Another way you can do it is you get a trouble light, you plug it into the, or some sort of light, you plug it into a socket, the outlet, and you just start flipping breakers until it shuts off. That method sucks, especially when you got 30 breakers in your house. Yes. Yep.
I don't think I've ever actually blown a circuit in my house.
That's good.
So how does the tracers work?
The tracers?
Yeah. Or you can plug them into a wall
Oh.
wall socket and then go to your circuit panel and just kind of run the meter up and down until it feeds.
So how those work is those actually send. So the thing is, you have to shut your main power off, and then what it does is it actually sends a signal in that line. So it usually sends like a pulsing signal, an AC signal, and so that way when you pick up the receiver, that's what you're picking up is you're detecting this change in current, and that's what makes the receiver squawk. And so that's good for tracing out lines if you have your power shut off to start with. But if your power's on, it's kind of hard to find it sometimes. We've done that before with some of our other outlets in my older house. They were wired all sorts of crazy. Like there was one outlet in the living room that was wired, and that was tied into 2 outlets in the front bedroom, 1 outlet in the back, and all the basement outlets. Like what the actual hell? Like I really wanted to slap whoever wired that house. I'm like, 1 room per plugs. We have 1 room that's plugs, 1 room that's lights. Plugs and lights, 2 breakers. Because it just makes things a lot easier when you're trying to fix stuff. Also, the big thing is when you're working on circuits like this, always shut the breaker off. If you don't, you will get bit. My furnace was working on it the other day. It kept coming up with a ground fault when we plug it into an extension cord that we had. So it's supposed to have some power wired to it by itself. We haven't had the electrician come out. They haven't had a chance to come out to run one from our circuit breaker to it. So we're using one of the outlets in our basement. We don't use these outlets very much, so that's the only thing on the circuit. It's not that big of a deal right now. But I was trying to rewire the switch, forgot to go shut the breaker off. So we're sitting there, and I'm messing around with it, and I'm rewiring the plug so it's working right, so it's not giving me the line fault. And I reach across, and I grab across the 2 hot wires. Zapped the crap out of me, yelled, threw my wrench across, or my screwdriver across the thing, hit the wall. My wife goes, "Are you okay?" I'm like, "No." She's like, "What's wrong?" "I got shocked." You know what her response was? "Haha, that sucks." Then I think the next words that follow was, "Dumbass." Because she knows I'm in this program. You always shut the breakers off before you work on a live system. There was 0 sympathy for me, but it was great. It was well deserved. But yeah, so that's the idea behind parallel is everything has access to the 120 volts, and then everything, all the current that we use is going to be combined together for our total. So our voltages are going to be the same for whatever's in parallel. Not necessarily the individual components, but what is in parallel from top to bottom is going to have the same voltage across it. So they have access to the same voltage. And then they use it based on the current. So voltages are going to stay the same. Current total will be your I branch 1, I branch 2, I branch 3, so on and so forth, to however many branches we have. This is kind of the shorthand for, and so on and so on and so on until we get to the maximum number. Our power is going to be equal to the power in branch 1, the power in branch 2, power branch 3, so on and so forth as well. So power doesn't change. It's always added together. The big difference between series and parallel circuits, and like I said, you guys are going to hate me, we find total resistance just slightly different. So in a series circuit, we add the resistances together to get our total. In parallel, it's equal to the reciprocals.
How does that make sense? R1 plus R2 plus R2.
So any resistance you have in parallel, you're going to use this reciprocal method. So you take the reciprocal of the value, add it together, and then take the reciprocal of that. The idea behind this is in parallel, resistance, so resistance in general is the opposition to current. When you get into parallel, you have two different aspects of work. You have your resistance, but you also have your conductance. So conductance is the ability of a material to conduct electricity. So the higher the conductance, the lower the resistance. So what we're doing here is we're adding up the conductance of each of these materials, each of these resistors, getting a sum total of that, and then converting that back into resistance. So one way to look at this is we're taking the sum of how well everything's going to conduct versus just adding everything straight together. Because if you add more resistance to a circuit, you're going to decrease how much it can actually conduct. That's the whole idea between a resistor.
So we're taking the opposite of conductance.
Opposite of resistance, adding them together, and then taking the opposite of that to turn it back into resistance. It's a lot, I know. Yes, we'll do a problem with that. So this is the base idea. This will work every single time. We have a couple of special case conditions that we can use that streamline this process. Okay, if we only have two branches, we can use the product over the sum rule. So in this case, we have R1 times R2 divided by R1 plus R2. This will give us the resistance total, only using two branches. Another one that we have is if we have the same R values. So if they have two resistors that are the same in parallel, we can use this one. You take the resistance value of one of them and you divide it by the number of resistors there are. So if we have three, so we'll go through some of these and we'll show you guys how they work. Okay? So the idea, we have a circuit. Come on. Okay, so we have 5 volts, and we have 100 ohms, and we have 100 ohms. We'll go through each of these steps and show us how to use all the different formulas. So in this case, we have two resistors and we have the same value of resistors, so we can apply all three of these rules. So using the reciprocal method, we would take the reciprocal of 100 plus the reciprocal of 100. We punch that into our calculators, and what do we get? So again, this is going to take lots of parentheses. What I like to do is I'll do one group of it to the -1 plus 100 to the -1, and then the whole thing to the -1. Or if your calculator doesn't have this button, it's the 1 over x. 50. Do people agree with that? Disagree with that?
I got 100, 100, something.
100 100ths.
Yes.
Yep, and then you're going to take that last answer and do the reciprocal of it. And that'll flip it over.
Yeah, I got 50 finally. I got after 4 tries.
Yep. Okay, so like I said, we use the reciprocal method. We take the inverse or the reciprocal of each of these values, add them all together, and then take the reciprocal of that. Okay, so that's the first way to do it. The second way is we take the product over the sum. So we take 100 times 100 divided by 200. That gives us 50. Yep. And then the last method we have as well is we take the value of one of the resistors and divide it by the number of them that we have. That also gives us 50 ohms.
So hold on, but if you have more resistors, you're going to have less total resistance.
Yes.
Why?
That's just how they work in parallel. Because remember, they're sharing the same voltage, and the currents are what's going to be changing. So the current's changing, resistances, for that aspect, not going to be changing.
That's why, like, when you put in the power supply and you check it for voltage, if you don't take the negative out, that's why it affects your circuit so much.
Yep.
Because all of the resistors in the power supply are in like parallel and series, so it also impacts.
And so the exact physics is why this is, I don't know. I'll be honest. That's still something I'm trying to research and figure out exactly how to explain the physical parameters of why this does what it does. I don't know at the moment. But I do know that as you put more and more things in parallel, that's your resistance is going to get smaller and smaller. So the idea to understand behind this is whatever we put in parallel, it's going to be smaller than your smallest value. You're never going to get a value larger than your smallest resistor. So no matter what we did, do what? Depending on what you're trying to do. So the thing is, when you measure, we'll show this in lab tomorrow, but when you get your DMM, or maybe I can do it here after a break, but when you get your DMM, you can grab another DMM and measure when you're in the voltage mode. You can see how much resistance is in your meter. And your meter should be around 10 meg. So the idea here is, so let's say, going with that idea, we put our voltmeter in parallel with this guy. So remember, when we're dealing with voltmeters, we want to try and get as small of a current as possible because we're going to be leeching off that amount of current. So if we can get a very, very small current, like 1 microamp type of a thing, leeching off of this guy. So with this, we have 5 volts, we have 50 ohms. This is, look, what is our total current? 100 milliamps. Okay? Yep. So we have 100 milliamps. Okay? Coming through, these guys are the same, so they're going to split, and I'll show you how the math behind this here in a second. But our current is going to split up between these two components. So we're going to get 50 milliamps through here and 50 milliamps through here. So when we hook up our voltmeter, let's say we're taking 1 microamp, it's going to split it, or it's going to take 1 microamp through there, and then the rest of this is going to be kind of split up between it. So we end up with, let's see, 49.998 milliamps. And in a sense, that's what we're doing. And the reason we're doing this. So we still have the 5 volts. We have the 1 microamp. But this resistance should be greater than 10 meg. Because remember what I said about things being put in parallel. It's going to be smaller than your smallest value. And if you can make this guy really, really, really large, it's not going to affect these resistors much at all. So if we were to look at this, now we have 3 branches, so we got to go back to this. So if we wanted to find what our R total is with the meter,
Yeah, so because the first two are the same, could we still use the amount of the number of resistors? And
yes.
then do the
Yes.
amount of after?
Yeah, when you're doing them in parallel, you can do these in any order. So if you have resistors that are the same, knock those out right off the bat. So yes. So essentially between these two in parallel, we have 50 ohms. 50 ohms is now in parallel with 10 meg. So let's run that through our calculations and find out what it's going to be. So either method you can do. Huh? 10 meg, yes. What does that value come out to be? 49.9999999 probably goes out for, yeah. How many nines do we have? 6 nines. Okay. The amount of variation that we're going to get is so small. That's why when you're doing your meters, you want that value, the ohms per volt type thing, you want that up as high as possible because you don't want to be affecting your circuit when you're measuring it. The worst thing you can do when you're going to measure your circuit is have an inadequate meter that's going to load down your circuit. Because let's say this guy wasn't 10 meg. Let's say he was 1K. What does our total resistance in the circuit do? Okay, so now this is with 10 meg. And this is now 1K. What'd you say?
49.75.
So the meter, even the meter that we designed in lab, isn't 10 meg. It's going to be a little bit higher than 1K. What was the total resistance you guys were getting through your circuits? Like what was your R1 value for those who have done it so far? Mm-hmm. So about 1,000 ohms. So if you're on your first setting, that's all the resistance you would have in this guy, measuring your voltage across it. So now you put a 1 kilo ohm load in parallel with 50 ohms, you've cut your resistance down by 40%, which means your current is going to go shooting up through the going to jump up 40%. If you have a fuse or current sensitive parts or power sensitive parts, that could be enough to actually pop your fuse in the circuit that you're measuring. So even though you're taking a measurement, you still can affect your entire circuit and screw it up. So that's one of the reasons, like I said, with these guys, you want those values to be as high as you can get them compared to what you're measuring things with. So, like I said, in parallel, I'm not sure the exact physics reasoning behind that. That's something I still need to go back and research, and I'll try and get an answer for you guys. No guarantees that I'll get to the point where I can explain what's physically going on. But one thing to remember too is that electronics or electrical signals are lazy. They're going to take the path of least resistance. That's why you get more current through smaller values. Even compared with these guys, I know these values aren't going to quite match up mathematically, but if we have 1 microamp, we're going to have huge amounts of current versus, or huge amounts of resistance versus low resistance. We get high current compared to everything else. Does that kind of make sense? Like I said, it's going to be kind of a hard thing to kind of wrap your mind around. But when we deal with resistors in parallel, we have to treat them differently because they act differently. And then when you're solving for things, make sure you keep that rule of thumb in mind, is that you can't have a resistance larger than your smallest resistor in parallel. Does that make sense? Okay. Let's do some more examples of this. Kind of help start driving this guy home. Like I said, the reason behind it is we want to use series circuits when we want to be able to control how much voltage each system gets. So if we have different LEDs, fans, whatever, we can wire them up in such a way that they're going to split up voltages equally. Parallel, we're going to use because we want to control the amount of current going through a device. Do they have access to the same voltage? We can then control individual currents going through them. And okay, so we have 25 volts. %90 of the time when we do circuits, I may forget to put the node points in. Very, very rarely will I have wires that are met together that don't connect. So in this class, just so you guys know, so all these connections are going to be a node. They will connect, even if I don't necessarily put the dot on there to indicate it. We're just not going to have a lot of circuits that have overlapping lines. So, looking at this circuit, we need to find out what our resistance total is, what our current total is, the current through R1, the current through R2, the current through R3, and we'll talk about the other values. So keeping in mind, voltage is going to stay the same in a parallel network. Currents will add together to get our total, and we use the reciprocal methods to find the actual resistance values. So to start with, what is the voltage across each one of these resistors? 25 volts. When you go up and measure this guy, you should be able to measure 25 volts across every single one of those.
So current total is still just going to be voltage divided by resistance, right?
Yes. Ohm's law still stays the same. And like I said, I go back and forth on which direction current flows. Just as long as you keep it the same through your entire circuit, it's fine. It doesn't matter which direction you go. So first things we need to find, a couple things we could find, either our R total first, or we can solve for the individual branch currents, then get our current total, then we could use that information to calculate what our resistance total is. And we can go through that and verify both directions. So first step, let's just go through and solve for the individual branch currents. Okay? Remember, current It's voltage divided by resistance. 25 volts, 1.1 kilo ohms. So what is our current? Yep, divide them. Yep. Yeah, so IR1 is equal to the voltage drop across R1 divided by the resistance value of R1. So what do we get for IR1? 22.72. Okay. What about for R2? Okay, so first of all, let's look. Does our answers make sense? 3.6?
Yeah, 3.6, right.
That's what I warned you guys about. One more time, 6.3? 3.6. I warned you that. I flip those numbers all the time. So if I do that, make sure you catch me on those because I try to do it. When it gets right to numbers, I'm a little bit dyslexic sometimes. Okay, so what did we notice here? Resistance went up, current went down. Okay, even more noticeable, what happened to the resistance? It doubled. So the current went down by half. Exact same ratios. Okay, R3. How? Okay, so again, we have our resistance went up by, compared to R1, 3 times. You take this number divided by 3, you're going to get that value. So just like we would have with voltage drops in series, if you increase your resistance by 2, 3, 4, whatever, your voltage drop is going to increase by 2, 3, 4. Same with the current. It's going to decrease by half because resistance and current are inversely proportional and resistance and voltage are directly proportional. Okay, so now that we have those individual currents, now we need to solve for our I total. Now remember Kirchhoff's current law. We have current coming into a node has to equal the current leaving a node. So if we look at these two guys right here, this node and this node, we have the current from R2 coming up, we have the current from R3 coming up. So how much current do we have leaving this node? Yep. And that is how much? Okay. So, and the reason that we know that this section up here coming out of this node is flowing this direction is because look at your inputs and your outputs. We have 3 connections. 2 of them are going in, so which means we have to have current going out. So we get the 18.935 milliamps. We have 22.72 milliamps coming up. How much do we have coming out? $71.655? 41 milliamps. Okay, so that's using Kirchhoff's current law and Ohm's law to solve for this guy. Now we have this value. We could also go back through and we could solve, so now we have this. So let's find our R total because we have our voltage total and we have our current total. So R total is going to be equal to voltage divided by resistance. So we got 25 volts divided by the 41.655 milliamps. What does that give us? Huh? 600 ohms? Okay. So that's going through by using Kirchhoff's current law to solve for this guy. Do we agree with that? Disagree with that? What do you think, Reed? Oh, that should be an I. Sorry. Yes, it's supposed to be an I, not an extra R. Magic. Okay, yeah, so resistance, remember, is voltage divided by current, not, throwing another resistance in there to solve for itself. So we have 600 ohms by calculating based on our current flows. Okay? We could also go through and we can solve this by using one of our formulas. Now, do we have any values that are the same? Nope, so we can't use that one. Do we have more than 2 branches? Yes. So we could use that method twice. Take 2 branches, do the product over the sum and get a combined total. And then we could do that again for that one. Or we could just do it all in one fell swoop. It just depends. We'll just do it in one fell swoop. So when we run that through our calculator, what do we get? 600 ohms. And we can also double check. Is 600 smaller than our largest resistor value? Yeah, smaller than our smallest resistor value. Yes. So we've satisfied that requirement. So now the whole thing we can reduce, we can combine all these resistors down into one single resistor, and looking at it, we would have a total of 600 ohms of resistance in the circuit. If we built this, put in a 1.1, 2.2, and a 3.3K in parallel, removed our power supply, measured it, we would get 600 ohms of resistance. Ish, depending on their values. Remember the difference too is when we're in class, we're talking about theoreticals. So the values that we're going to be used are going to usually be spot on as far as like their values. When you get into lab, your 1.1K is not going to be 1.1K. It's going to be 1.0K, 1.02K, things like that. Use those values that you actually measured when you're doing your calculations for lab. Because the difference is theory and lab. Theory is perfect world. Lab is application of perfect world principles in an imperfect environment. So you have to account for those losses, account for the differences, and when you do, like I said, your measurements will line right up. Okay, so that gives us, like I said, I wanted to go through both ways because that gives us our R totals in both directions. We can either solve it first, or we can solve it afterwards. So same thing, then we could come in through here, and we could find out our current total. So the current total, get back up there, really? Stay. How much did you say? Okay, and again, it comes down to the rounding, what our calculators did. I'm not too worried that we're, 12 microamps difference. Yes, Reed. Oh, no, you're good. I just looked down the corner of my eye and saw a hand, so. Okay, so once again, we're able to prove that we're getting the same numbers going either direction. Now, one of the cool things is, remember in a series circuit, what tool do we have to solve for voltages? I don't want to give the initials because it makes it sound dirty. Voltage divider. Okay? So remember, voltage divider is this. The resistance value of whatever one we're looking for over the resistance total multiplied by the voltage total. That's how we use voltage divider. Well, in this case, the voltage isn't what's getting divided. What is? The current. So in series, we have voltage divider. In parallel, we have current divider. We'll go with that. Is it ER or OR? ER? Okay. I'm also not the world's greatest speller either, so. So we have current divider. If we want to find the current through branch whatever, it's equal to the current total times the resistance total over the resistance of branch whatever. So we flip the ratio when we're solving for current divider. So this way, we could have come in and said we have a total of 41.667 milliamps. We could have worked backwards and said how much is going to flow through each one of these circuits, or each of these branches. So in I branch 1, which is going to be the current through R1, we take our total current, we multiply it by the resistance total, which was 600, and divide that by that ratio. We're going to get, what do we get when we multiply those guys together? .7 milliamps, which is what we calculated up there, just by using Ohm's law. So either way we can get to this. We can go through for multiple directions of attack on this guy. The biggest thing I wanted to show is we have these shortcuts that we can use, these not shortcuts, these tools that we can use to solve for these guys. There's going to come a time where current divider and voltage divider won't work, but that's when we get into phase angles and things like that with capacitors and inductors, resistors in AC portion. Current divider, voltage divider does not work anymore because we have to worry about phase angles. We'll do other math for that. But the idea behind this is when we're dealing with just one set of devices, resistors or capacitors namely, we can use these formulas interchangeably because we don't have to worry about the phase angles. When we get into inductors, that becomes a little bit more tricky. But we have these tools that we can use real quickly to kind of see how is our voltages going to break up across these guys. So use them, understand them. The whole idea is we're just trying to find the ratio of how much our total resistance is, basically what portion of the total current is each branch going to take. Okay, any questions right now? Okay, let's go ahead and go to break. When we come back, we'll work some more through these circuits.